Hey everyone, welcome back, and let's write some more neat code today. So today let's solve first missing positive. This is a hard problem, not because it's hard to solve. There's a variety of solutions. One solution is an n log n solution. Another solution is a linear time solution, but that one takes also linear time memory as well. So time and memory, but there's also a solution with linear time, but it takes constant memory, and that's the difficult solution to create, which is why this problem is categorized as hard. That's the one I'm going to be mostly going over today. So we're given an unsorted integer array of nums. Simply, we just want to find the smallest missing positive integer. What does that mean? Well, my question is, what's the smallest positive integer in general? What's the smallest positive integer? 1, right? That's pretty simple. We know that 1 is the smallest positive integer. The second smallest is 2. The third smallest is 3. So we want to know, given an input array of nums, it's not sorted necessarily, but we want to know what's the smallest. So initially we're going to say, without even looking at the array, we're going to say, well, the smallest possible could be 1, right? So let's iterate through the array now. First value 1. So okay, the solution is not going to be 1. Maybe it's going to be 2, right? Let's go to the next value. Oops, there's a 2 here, right? So next smallest possible could be 3. We go to the next value, it's a 0, right? That's not a positive integer, so we don't care, right? And it's definitely not a 3, so we don't care. So now we've run out of the array. What's the smallest missing positive integer? 3, right? We were keeping track of that, so we're going to return 3. So basically the way I was going through the problem right now is one way you could solve it. But to solve it in that way, you would need to sort the input array in ascending order. So we're going to sort of be greedy here, right? We're just going to say 1 is the smallest positive integer that's missing, right? And since we know our input array is sorted, we know that if there exists a 1, then clearly we were wrong in our assumption, right? So in this case, we do see a 1, so we were wrong. So then we'll change what our solution is to a 2, right? And then we'll see a 2, and then we know we were wrong again, right? So then we're going to change our answer to a 3. We're going to say, okay, maybe 3 is the smallest missing positive integer, and then we're going to get to a 4, right? And so once we've gotten to a 4, we know every value that's going to come after it is going to be greater than or equal to 3. So at that point, we basically know, yes, 3 was the one that was the smallest missing positive integer. Now, the time complexity is going to be n log n because we are sorting this input array. But one thing to notice with this is, see the size of our input array. The size of the input array is 3, right? So that means in the worst case, the smallest missing positive integer in the worst case, right? In the largest it could possibly be is going to be 4. Why is that? Why is it going to be 4 in the worst case? Well, take a look at this. What if the input array we got was 1, 2, 3, right? Remember, the size of our input array is limited to size 3. So in this case, if we had 1, 2, 3, then we know that n would be 4. The result would be 4 because we're missing, the smallest positive integer we're missing is the 4 that would go here, right? If, for example, we did not have all 3 of these, right? Maybe we're missing that 3 like we had previously, then we would have the n equals 3, right? Or for example, maybe we would be missing a 2, right? Maybe we have 1, 2, 3, 4. Then in that case, we'd have a 2 that goes here, right? 2, 3, 4. Then in that case, the smallest missing is going to be 1. But basically, no matter how you arrange this, right? Maybe we would just have really big integers. For example, 10, 11, 12. What's the smallest missing in that case? Again, that's just going to be n equals 1, right? So basically what I'm saying here is no matter what our input array is, no matter what the values go in it, the answer, our result, n, the smallest missing positive integer, is going to belong to the set between 1 and length of the array plus 1. That's pretty obvious, right? That's mathematically obvious, right? We could not have a smallest missing positive integer that would be larger than this if our input array is just, limited in size. We could not have a missing positive integer. So this is our solution set, right? And we're given that based on the length of the input array. So in reality, we actually don't need to sort this input array. We can actually take the input array, convert it into a hash set. Why are we converting it into a hash set? Because we're going to brute force this. We're going to go through every single value from 1 to n plus 1, right? Or the length of the array plus 1. So we know the solution belongs to this. We're just going to have a for loop that goes through all of these values, tries each of them, right? So for example, we're going to try n equals 1. We're going to check, does n equals 1 exist inside of our hash set? And we can check that in O of 1 time, right? If it does exist in our hash set, then we're going to try n equals 2. Right? If that exists, then we're going to try the next number, right? N equals 3, so on and so on. If n equals 3, for example, does not exist inside of our hash set, then we're going to return n equals 3 as our result, the smallest missing positive integer. If, for example, we go through the entire loop and we don't find any value, so for example, if we tried the n equals the length of the array, and even that was found in the hash set, then by default, we're going to return n equals the length of the array plus 1, right? This is our worst case scenario. This is the largest it could possibly be. And so since each of these operations just takes O of 1 time, and we're doing it for every value based on the length of the input array, this is going to be 1 times n. That's just big O of n time complexity. But the hash set is taking extra memory, right? So that's going to be big O of n memory as well. But we can use this to our advantage. We can devise a way where we actually don't need a hash set. How can we do that? Well, we are going to need some extra memory, but it turns out we can use this input array as that extra memory, so it doesn't actually count as extra memory. So we can take this time complexity, or this memory complexity, big O of n, and reduce it all the way down to big O of 1 by using the input array as our extra memory. So like I said, we're going to be using the input array as extra memory. Just like we used an extra memory hash set, we're going to basically be using our input array as a hash set. How am I going to do that? Remember how our solution set is basically from 1 all the way to the length of the array plus 1, right? This is our solution set between 1 and the length of the array plus 1. So for every value between 1 and the length of the array, right, we have an index for that, right? So 1 is going to be mapped to the 0th index, right? 0 index, 1 index, 2 index, 3 index, right? The last value, length of the entire input array, is going to be mapped to the length of the array minus 1 index, right? So in this case, we can see the length of the input array is 4. So 4 minus 1 is going to take us to this index, right? So each of these values has a position in the input array. So how am I going to use the input array basically to tell us, for example, if I want to know in constant time if the value 2, right, the value 2, does 2 exist in our input array? How can I know that in constant time? The way I'm going to do it is I'm going to say, okay, we want to know if 2 exists. I'm going to take 2 minus 1, right? That's going to give us our index value. I is going to be 2 minus 1. We know that evaluates to 1. So we're going to go to the 1 index, right, which is over here. This is 0. This is 1. And we're going to go here and we're going to check, is this value negative? Negative tells us that 2 exists in our input array. We don't know where it exists, but we know that 2 does exist. We can figure that out in constant time, right? So we're going to use negatives to determine that. Just one problem. It turns out that this input array that we're given can have negative values by default. So how am I going to handle that? Well, it turns out we're looking for the smallest missing positive number. Obviously, by just looking at this, we know that that's going to be n equals 1. That's going to be the result, right? But we're looking for an algorithm to solve this problem. And it turns out that negative numbers are useless to us. We don't really care. If I took every negative number inside this input array and just crossed it out, it would not matter, right? So that's exactly what I'm going to do. I'm going to take every negative number, for example, negative 3, get rid of it, replace it with a 0. Why am I doing a 0? Why don't I just replace it with a 1, right? Well, in that case, if I replace it with a 1, I just changed the entire input array, right? Remember, the solution to this problem is n equals 1. If I add a 1 to this, then I've changed the solution to n equals 2, right? We don't want to do that. That's why we're giving it a neutral value of 0, right? I'm replacing every negative value with a 0. So it might be a little messy, but let's just assume that this has been changed to a 0. So we're going to basically scan through the entire array, change every negative value to a 0. We can accomplish that in O of n time, and we're actually going to be needing to scan through the entire array 2 more times, so it's overall going to end up being 3 times n, but that's still linear, right? That's still going to reduce to big O of n. And since we're not using extra memory, we're using the input array as extra memory, the overall memory complexity is going to be big O of 1. So now what I'm going to do is I'm going to start at the beginning of the array again, and now is when I'm going to start marking values as appearing in the array. For example, 3, right? We have a value 3. We want to mark that 3 exists in our input array. So what we're going to do is we're going to go to the index I equals 3 minus 1. That's index 2. Index 2 is over here, right? And we're going to change this value to a negative value if it's not already negative. Right now we see that it's positive, so what we're going to do is we're going to change it to negative, right? So we're just going to add a negative sign. This is going to be negative 6 from now on, right? So we are changing values, right? So it turns out that it's possible that this also could have been a negative 3, right? So basically every time we get to a value, we're actually going to be taking the absolute value of it, so absolute value of 3, and then minusing 1 to find the index. So since index 2 is negative, we know that 3 exists in our input array. Next, we're going to go to this value. It's 0, right? It turns out I equals 0 minus 1. That's going to be negative 1, right? That's out of bounds of our input array, right? That's going to be over here, right? That's out of bounds. So we're not going to be filling values that are out of bounds. So it turns out this is out of bounds. We're not going to fill it. Next, we get to the value 6, but remember this is negative 6 now because we changed it, so we're actually going to have to take the absolute value of this. Absolute value of negative 6 is going to be 6, right? So we're going to get I equals 6 minus 1. That's going to be 5, right? So again, we went out of bounds, right? That would be somewhere over here, but that's out of bounds, right? So and we know this would never be the solution anyway because it's too big. So okay, and then we're going to go to the last value. Again, we found a 3, right? So we're going to go to I equals 3 minus 1. That's going to be 2. We know index 2 is going to be over here. So, and we're going to change this to a negative, but good thing for us, it's already negative. If it's already negative, we don't want to change it back to a positive number because remember, 3 does appear in our list. Just because it appears twice doesn't mean we want this to be positive. We still want to know in constant time that a 3 exists in the input array. So we leave it negative. So then one last time, we're going to be iterating not through this loop. Now we're going to be iterating through this set. So we're going to be iterating through 1 through the length of the input array A, right? So that's also going to be an O of n operation, right? Basically the length of this input array. So we're going to start for n equals 1, right? We're going to take 1. We want to compute the index, right? So we're going to take 1 minus 1 is going to be 0, right? So we want to know, does 1 exist in our input array? We can check that by checking the 0th index of our input array. If it's negative, that means 1 does appear in the input array. If it's positive, which in this case it's positive, right? This is positive 3. That means n equals 1 does not appear in our input array, right? Therefore, n equals 1 is the smallest positive integer that does not appear in our input array. Awesome, right? That's the solution. We did that with 3 loops, but it still ended up being big O of n. There's one last edge case that I'm going to show you. Notice how this value was originally a positive 6, right? But we changed it to a negative 6 because we still wanted to know what value was originally stored here, right? So we could take the absolute value and then convert it to a positive 6, right? We wanted to know the original value. But we also wanted it to be negative so that we could indicate that a positive 3 exists in our input array, right? But my question to you is, what if the value that we're changing, for example, What if we had one more value in our input array and it was a 2? Then we want to mark that 2 exists in this input array. So we can compute I equals 2 minus 1. That's going to be 1. So we're going to go to the 1 index value in our input array, right? This is index 0. This is index 1, right? So now we want to mark that we want to change this to a negative value to mark that 2 exists in the input array. Hold on, this is a 0, right? But we don't like changing the value. We just want to multiply it by -1, but it'll stay 0. So what value can we change this to? For example, if I just change this to a -1, right, a -1 value, we can't do that. Why can't we do that? Because then we're changing the input array. Remember, this -1 will eventually, we're going to take the absolute value of the -1, right? And then basically we're assuming that a 1 exists in the input array, but originally there never existed a +1 in the integer array. So we can't change this to a -1. If we do that, we change the solution of this input array. So we have to change it to a negative value that does not affect the solution. But remember, the solution set could only be from 1 to the length of the input array. So if we change it to supposedly negative length of the input array plus 1, right? So basically we're taking length of the input array plus 1 and multiplying it by negative, right? If we do that, we're not changing the solution set, right? Well, actually, technically, this could be a solution, right? This would be the worst solution that it could possibly be, the greatest value it could possibly be. But notice with this value, it's out of bounds when we compute the index of it. So basically, this is a good default value to give it because we're never going to be marking that value as showing up in our input array because it's always going to be out of bounds. That's basically the point that I'm trying to make. So that basically handles all the edge cases. So if we found a 0, this is the negative value that we would give it to. Otherwise, we would just take that positive value and then multiply it by -1. So with all those edge cases being said, now let's actually jump into the code. It's going to be 3 linear time loops. So remember, the first thing I'm going to do is go through every value. And by the way, I changed the name of the input array to A just because it's shorter. We're going to be writing that a lot. I don't want to change it. I don't want it to be nums because I don't want to type that a lot. But I want to go through every single value. So for range of the length of this input array, if the value at that index is negative, remember, if it's less than 0, then we're just going to change it to be 0. That's a good default value to neutralize these negative values to. The next portion of this algorithm is going to be another for loop, just iterating through the input array. But this is the part where we're marking if a value exists in the input array or not. So we're overwriting the input array A. But remember, we're only doing that for values that are in bounds. So basically what I'm going to say is if our value at A at position I, index I, is between 1 or the length of the input array A, if that's the case, so if this is the case, that means it's in bounds, but it could technically possibly be negative because as we're going through the loop, we know we're going to be changing values to be negative. So we're going to take the absolute value of that, so absolute value of this, and we're going to store it in, let's say, value. Next, so we want to overwrite a position, right? So for example, we want to say A of value -1, right? Because we were taking the value, subtracting 1 to get the index. Right, so what we're trying to do is mark that this value exists. We're doing that by taking this and creating it to be negative. So what we're going to do is basically say multiply this by -1. But remember, we're only going to be doing that if this value is originally value -1, if it's positive, right? If it's positive, then we want to make it negative. If it's negative already, then we don't need to do anything. But the last case was else if this value happens to be 0, right? That was the edge case that we were worrying about. So if this happens to be 0, then what we can do is assign it to a special value of -1 multiplied by the length of the array plus 1. And that's actually this entire loop. So once this loop is done, we have basically, instead of using a hash set, we basically used our input array to mark which values between the range 1 to the length of the input array do appear in this array. So now we actually want to determine what the solution is. So I'm going to say for I in range from 1 to the length of the input array plus 1. Now we want to know if I does not exist in the input array. How do we know that? If A at index I minus 1, remember, so for any value, we're subtracting it by 1 to correspond to the index. So if this happens to be negative, that means this value does appear. If it's positive though, or 0, if it's greater than or equal to 0, that means I never showed up in the input array. That means I was the smallest positive integer that did not show up, because we're going in increasing order, right? We're starting at the smallest and increasing. So if this is true, then we know that I never showed up, so we can return I as the smallest positive integer. If this entire loop executes from 1 to the length of the input array and we never returned anything, that means the smallest positive integer must be the worst case integer, which happens to be length of the input array plus 1. Okay, I'm really sorry, but I just noticed I had a bug. Remember, since A of I could possibly be negative, we actually want to compute the absolute value of that A of I before we check this condition, because if it's a negative number, then we want to take the absolute value before we determine if it's between 1 and the length of this. So really sorry about that. And instead of checking A of I, we're of course going to be checking the absolute value of that. So this is going to be the correct solution. Really sorry about the explanation, but I hope that most of the logic still makes sense of what we're doing. But this video actually took me longer than I expected, so let's wrap things up. This is the entire code. Like I said, we have 3 loops, so I hope that this was helpful for you. This is a linear time solution and no extra memory needed if you don't count the input array, so O of 1 memory. If this was helpful, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.